Summer of 1940, Britain watched as the German Wehrmacht swept through France with relative ease. A month after France was secured, Nazi Germany shifted their sights to the north. In an attempt to compel Britain to agree to a peace settlement, Hitler began an air and sea blockade on the island nation, with the Luftwaffe targeting coastal shipping convoys and ports. On August 1st, Hitler commanded his Luftwaffe to achieve air superiority over the RAF, and their attacks shifted to RAF airfields and infrastructure. These attacks escalated into what would become known as Operation Sea Lion, which was planned as an amphibious and airborne assault on Britain with the aim of finally occupying the island. However, that operation was cancelled because Britain would not surrender. The nation would put up a legendary resistance that was a testament to the resolve of her people. Even more, when she was done defending herself, Britain took the fight back to the Germans and began fierce counterattacks in the form of night bomber raids. This first setback for the Wehrmacht in the Battle of Britain would prove to be the first errant strand that would ultimately unravel the entire German war machine. And one engine, more well known than perhaps any other of the war, was at the very center of that fight. An engine that perhaps came to embody the will of the entire nation with its ever-increasing performance and unrivaled dependability. And that engine was the Merlin. By the end of the war, the Merlin would have powered more than 40 different aircraft, including the famous Supermarine Spitfire, the Hawker Hurricane, the Avro Lancaster, and last but not least, the North American P-51 Mustang. Essentially, whenever a power plant was needed in an Allied aircraft, the Merlin became the standard with which all other engines were compared, and for good reason. Now, you might be forgiven for believing that Merlin was named after the famous wizard, but it wasn't. No, instead it was named after the falcon found in the northern hemisphere, of which there are two species, the North American and the Eurasian. In fact, the Merlin was the 9th Rolls Royce engine to be named after a raptor, but more on that in a bit. So, with this impressive resume in mind, we're left with some questions. Who were the men who made the whole process possible? And what was unique about the design of the Merlin? Why did it become the standard with which all other Allied engines were compared? But before we can answer those questions, we first got to answer the most important question of all. What did the Merlin sound like? Now, this is going to be a really quick run through the history of the company's formation, but if you want a more in-depth look, I recommend one of my sources for this video, The Merlin, the Engine That Won the Second World War by Gordon A. Wilson. In it, he gives a pretty exhaustive detail on the events that took place in the early days of Rolls-Royce, so again, check it out if you really want an even deeper dive. The Rolls-Royce company was formed by surprise, two men, Frederick Henry Royce, who went by Henry, and Charles Stewart Rolls. So, who were these guys? Well, to start, Royce was much older than Rolls. Born in 1863, he was kind of a badass from a very early age. At just 9 years old, he found himself on the streets of London, essentially taking care of himself because his father had died and his mother, for one reason or another, wasn't able to take care of him. So essentially, he started trying to make his way with periods of education mixed in with work until his aunt eventually sponsored him so he could become an apprentice at the Great Northern Railway. It was while working at the railway that Royce realized he was really interested in engineering, but soon after his aunt fell through and could no longer support him. So at 17, he found himself back at the grind. But realizing he wanted to design things for a living, he was soon employed by a toolmaker in Leeds, which is where he discovered that electricity is essentially real magic. So, enamored with the idea of working with electricity, he began a job with the Electric Light and Power Company in London, and would begin to study under William Ayrton and Hiram Maxim, where he would cut his teeth as a real engineer and begin to grow more aspirational about his future. Soon after, Royce would be confident enough to begin his own business along with his partner, Ernest Claremont, and at 21 years old, Royce would become co-owner of F.H. Royce & Company Electrical Engineers. So Royce has started his own business, which rapidly begins growing and providing people with little electric bell sets, and then grows into providing like larger items like current dynamos and electric motors. But probably because it was instilled in him from a very young age that if he was clever and worked his ass off, he could secure some serious social mobility, Royce quickly developed a habit of being such a voracious workaholic that he would literally make himself sick. Working for hours without eating or drinking, he would also stress himself out to the point he was nearly non-functional. Essentially, he was literally trading his health for business success. However, sometime after this period, as Royce found ways to manage his health in spite of his habits, Royce bought his first car, which would be that impetus for all that was to come. While he was inspired by the invention of the automobile in his own 10-horsepower DeKalb, Royce would soon realize he could have designed a better car himself. So, after talking to the board of directors at his company, he floated the idea of designing his own product. By taking the DeKalb and making incremental improvements, Royce soon had a vehicle unlike any other, and it was designed and built in England, which would eventually be the reason he would run into Charles Rolls. So, to put things into context, when Royce was 21 and striking out as an independent businessman for the first time, Rolls was just 7 years old. Born to a wealthy family, Rolls was essentially allowed to follow whatever pursuits he wanted with no obstacles from a very young age. Perhaps unsurprisingly, that interest would at first be motor cars, which would earn him the nickname of Petrols, as he was always tinkering with motors. His interest was so obsessive, actually, that we know that he had to cram to gain entry into Trinity College. But soon, Rolls' fascination with the automobile would lead him to France, where he would buy his first Peugeot Phaeton 3.75 horsepower car. Yes, horsepower was so hard to come by during this time that the extra 3/4 was notable, and in any case, Rolls was hooked immediately and brought the car back to England, where he would eventually become a founding member of the Automobile Club of Great Britain in 1897. And again, to put this into perspective, the car is a brand new invention, essentially only accessible to the elite at this time. So you can see what essentially becomes a fraternity of rich car enthusiasts forming in England who end up racing their cars and competing with one another. Also, at this time, Rolls gets his first taste of flight with the balloon ride, and he becomes equally, maybe even more obsessed with flying. But those opportunities are few and far between, even with his means, so it was back to car racing for a while. So what leads Rolls to eventually meet Royce and form what we know today as Rolls Royce was Rolls beginning a racing career in which he would take part in city-to-city races across the country, which were essentially part wealthy competition and part advertisement for the people around the country who had not yet fully accepted the automobile as the dawn of a new era of transportation. In them, there would be multiple events such as hill climbs, flying mile time trials, and match races. So racing automobiles essentially became Rolls' life for a while, but as he raced in his imported cars such as his Panhars and Moors and Minervas and Clermonts, Rolls soon realized there wasn't a solid domestic car for him to be proud of, and as such he soon became enamored with the idea of his name being associated with a car of his own. And wouldn't you know it, his engineer friend named Henry Edmonds happened to work with a guy who had recently designed his own car. So Rolls and Royce finally meet, and the meeting goes so well that in one afternoon they agree to go into business with one another and form the Rolls Royce Company, which would focus on developing and selling a 15-horsepower car that would be tailored toward a luxury niche. Rather than a race car, it would be a car his wealthy friends would love to own. So, with a rapidly growing product line, the two began designing a myriad of cars, eventually working their way up to a car known as the Silver Ghost, which became their 6-cylinder flagship product. In their business relationship, Rolls essentially helped advertise the cars by traveling around and racing them, while Royce stayed back in the shop, slaving away with his various design problems, which suited his personality well, save for the fact that he was still not taking care of his health. So during this time, between 1904 to 1910 or so, Royce was learning important engineering lessons about how to increase the power output of internal combustion engines, while Rolls began falling in love with aviation. After another balloon ride that narrowly escaped disaster, Rolls earned his aeronaut certificate and bought several of his own balloons. Soon after, he traveled to France and learned to fly a Wright airplane. Yes, Rolls was so early to the aviation show that he earned his pilot certificate on the literal very first powered airplane that existed, and soon after, he was absolutely hooked on flying. So naturally, he went back to Rolls-Royce board of directors and proposed that they form a partnership with the Wright brothers and begin manufacturing Wright flyers in Great Britain. But the board shot him down, not willing to take such a wild business risk. So, being the stubborn type, Rolls naturally resigns his position as technical director and sets out to pursue more aviation accolades. In the meantime, the Short brothers eventually picked up the contract to build Wright Flyers, and Rolls was one of the first customers. But the delivery would take an exceptionally long time, so he began flying a glider in the interim until finally receiving his very own Wright Flyer. Right after he took delivery of his aircraft, Rolls strapped it to a catapult that could launch the plane to flying speed while it sat on a trolley. On one of his first launches, Rolls, attempting to take off, pulled too much angle of attack and essentially performed a textbook takeoff stall, which crashed the plane. However, Rolls was unharmed. But this early upset really didn't matter to Rolls. He was so obsessed, he would go on to collect more qualifications, prizes, and cups for his flying longevity and distance, and continue to cut back his work at Rolls Royce even more so he could continue his new career as essentially an aviation proponent. As such, Rolls earned the second Aero Club's pilot certificate and soon began coordinating with the military about the future of aviation and wartime operations. Rolls' aviation career would peak when he would complete the first round trip to France and back in a powered aircraft across the English Channel. This two-way crossing, non-stop, was the first from England to France, and as such, Rolls was awarded the Royal Aero Club's Gold Medal and essentially became a national hero. From this point forward, his life would become that of an aviation celebrity. It was a whirlwind of wrecks and rebuilds and repairs and overhauls and flying competitions until July of that year. On the 12th of July, 1910, Charles Stuart Rolls was killed while flying his French-built Wright aircraft and became the first Englishman to die in a powered, heavier-than-air machine. Shortly afterward, while the country was mourning the hero's death, a memorial statue was unveiled in Shire Hall in Agincourt, Monmouth, and I don't know if I'm pronouncing that correctly. I'm sure you'll tell me if I'm wrong. With Rolls' death, Royce and the company placed a no racing policy in effect, and Royce began pouring all of his energy into redeveloping the 40/50, which is also known as the Silver Ghost, as his health continued to spiral. To keep him running, Johnson, his business partner, proposed that Royce spend his winters in Le Cannondale, France, and his summers in England, so he wouldn't have to face the harsh winters, and he might have a more relaxed work environment. The only trouble with this plan, however, was that email hadn't been invented yet, and so all communication took place through letters and parcels, telegrams, and personal visits. But if email had been invented, considering the importance of Royce's communications being integral to the company's future, he surely could have used some help from today's sponsor, NordVPN. As a career airline pilot, I travel a lot, and as an amateur YouTube historian, I also have a lot of stored data like passwords and other sensitive information I'd rather not lose. So that's why whenever I'm abroad, I use NordVPN to help me avoid man-in-the-middle attacks. Now, you might be asking, what the heck is a man-in-the-middle attack? Well, a man-in-the-middle attack happens whenever someone in a public space starts offering their own free Wi-Fi network for others to join. Now, that sounds very nice of them until you realize the only reason they're doing it is so they can gain access to your computer's data. You see, in the man-in-the-middle attack, the owner of the network has configured it in such a predatory way that whenever you join the network, the owner of said network automatically gains access to your personal files and essentially whatever it is you're currently doing. In that way, when you connect and say log onto your banking system, that information you've entered is stored for him to use whenever he'd like. So how does NordVPN help? Well, by encrypting your data on the fly, whether your connection is secured or not, you can use whatever Wi-Fi connection you'd like with little worry of who might have access to your files or activity. Essentially, instead of the attack working, you're just stealing his Wi-Fi, which is like karmic justice, right? And that's not the only thing NordVPN does to protect you. By using NordVPN threat protection, they can also help prevent other types of attacks, such as phishing attacks, password attacks, DDoS, malware, and ransomware, to name a few. So to be as well protected as possible, use our link at NordVPN/FlightDojo to try NordVPN with a 30-day risk-free money-back guarantee. Again, if you're sending any privileged or sensitive information all over the internet in 2022, you need a VPN. Also, I should probably mention that you can use VPNs for other cool stuff, like changing your virtual location to other countries to look for better deals while you're online shopping, or to watch shows that maybe aren't available in your country. So if you're on that fence about a VPN in 2022, head over to our link again at NordVPN/FlightDojo and give it a try. However, there is one thing NordVPN can't yet protect you from, which is artillery shelling, which is why in 1914 Royce was forced to move back from France to England as World War I had properly begun. Up until this point, Royce had avoided aviation altogether with his company, but if Royce wouldn't flock toward aviation, it would soon find him. When war broke out, planned production cutbacks were immediately canceled, and a collection of 40-50 cars were converted into armored cars instead. However, most importantly to us Merlin fans was that the British government forced Royce into the aviation business when they asked him to manufacture the Renault V8 and the RAF-1A Aero engines. In true Royce fashion, however, he did exactly what he did with his first car and immediately claimed he could build a better Aero engine than these examples. Soon after, the horsepower race that would last until Royce's eventual death would begin, as Royce threw himself at the design of a new 200 horsepower Aero engine. Borrowing from the Mercedes DF80 engine and the Renault, Royce eventually unveiled the first Rolls Royce Aero engine, the Eagle, a liquid-cooled V12. The Eagle essentially was a redesign of the 4050 engine that borrowed the top end from the DF80 and the connecting rods of the Renault. The result was a 60-degree four-stroke engine with two banks of 6 cylinders and a capacity of 20.3 liters. By 1918, the Eagle would generate 360 horsepower and would be installed in 50 World War I aircraft. The company would also manufacture the Hawk, which was essentially a scaled-down version of the Eagle with only 6 cylinders. The next engine that would form the pedigree that eventually led to the Merlin was the Falcon, which was essentially a medium-sized variation engine. Essentially, it was a 14-liter version of the Eagle that generated about 270 horsepower and was used in famous aircraft such as the Bristol F-2B, which, for the record, is probably my favorite World War I aircraft. Two other RR engines were designed just after World War I. The Condor and the Eagle 16 were also produced before the next big stepping stone engine for the company. The Condor essentially was a scaled-up version of the Eagle, generating 500 horsepower at 35 liters. However, its large cylinders required 4 valves per cylinder rather than the Eagle's 2. In addition, some of the first aero streamlining design choices were made with the Condor, as they had relocated the oil and water pumps within a single unit underneath the engine. The Eagle 16, which had no relation to the original Eagle, was an experimental X engine which made 500 horsepower on 20 liters, but was rejected because the aircraft industry believed the X arrangement would restrict the pilot's visibility. The X design would be revived, though, for later engines such as the Vulture and the X. The Rolls-Royce Kestrel would be a huge step forward for Rolls-Royce. With a single aluminum alloy monoblock, 4 valves per cylinder, and a dry sump, the F-10, as it was originally designated, was a direct-drive, extremely compact power unit. Now, rather than the Condor, which generated 500 horsepower with 35 liters of displacement, the Kestrel could generate the same power with only 19.8. In 1930, the F-type engines were renamed the Kestrel series, of which the numbers 1, 2, or 3 indicated the gear reduction ratio, and the suffixes A or B indicated compression ratios, and whether the engine used a medium or full supercharger. By the end of Kestrel development, the engine had graduated to 745 horsepower at 3,000 RPM. Interestingly, while domestically the Kestrel was installed in 15 British aircraft, it was also installed for testing purposes in early variants of the Bf-109 and the Junkers Ju-87. However, as we've become accustomed to hearing on this channel, the quest for more power continued. And with it came the next engine in the Rolls-Royce lineup. Known as the Buzzard, the H-block engine was bigger and more powerful than the Kestrel. Also, its supercharger could be used to its full extent on the ground, enhancing takeoff performance. It first ran in 1929 and was 50% bigger while generating 50% more power than the Kestrel. The final numbers were 955 horsepower on 36.7 liters. Now, this was a huge leap in specific power and engine efficiency. However, the best was yet to come and would be spurred on by good old-fashioned competition. In 1912, a man named Jacques Schneider wanted to spur on the development of seaplanes, which he thought were falling behind their air-based counterparts. As such, he started the annual Schneider Trophy race, in which enthusiasts could enter their aircraft to race for a 1,000-pound prize. The race was significant in advancing airplane design, particularly in the field of aerodynamics and engine design. As such, Rolls-Royce, wanting to make a bigger name for themselves, teamed up with Supermarine to create the ultimate race plane. The result was the Supermarine S6, which, hidden under its streamlined cowling, was a monstrous Rolls-Royce Type R engine. For the same weight as the Buzzard, the R engine tripled the horsepower available. But increasing power by 265% doesn't just happen without some trade-offs. So how did they achieve this? Well, by tuning the engine to a state in which, in its first form, the engine only had a lifespan of about 20 minutes. Essentially, Rolls-Royce discovered that by using specialized fuel, a customized crankshaft, connecting rods, and crankcase, they could create an absolute monster of a power unit. And as such, the S6 easily won the race in 1929. But it would come back to win again in 31, featuring an increased engine speed, more aggressive supercharger ratio, and a bigger air intake. In this configuration, the R engine's final rating was generating 2,530 horsepower on 36.7 liters, which was a massive output for its time. So much so that the engine would be the only engine in history to power the world's fastest car, boat, and airplane at the same time. It was also the engine that taught Royce several important lessons related to designing engines with massive power outputs. These lessons included knowledge of metallurgic alloys required, as well as others such as issues relating to high oil consumption and engine vibration. The final engine Rolls-Royce would produce before the Merlin was the Goshawk. Originally known as the PVG, which might have stood for the Private Venture Goshawk, the engine used an evaporative cooling system, which was more efficient in removing heat than a traditional liquid cooling system. However, the need to use a condenser to turn the coolant back into a liquid created a large amount of aerodynamic drag, being more bulky than a radiator. Also, the realization that any damage to the system in combat would be catastrophic rendered the Goshawk project canceled. However, the engine did produce respectable specific power for its day, generating 600 horsepower on 21.25 liters. Finally, in 1933, the engine that would become the Merlin appeared on Royce's drawing board. The Kestrel, which had become essentially their flagship engine, was at the end of its development life, and as such, a new leap forward was required. This leap would at first become known as the PV-12, or the Private Venture 12, as the government had not yet subsidized its initial development. The idea was to use all of the lessons they had learned with the R engine project and attempt to find a middle ground between performance and reliability. The resulting design was a 60-degree liquid-cooled monoblock displacing 27 liters and featuring a 5.4-inch bore and a 6-inch stroke. Originally, like the Daimler-Benz series of engines, Royce proposed an inverted V design, but this idea was rejected as too out of the ordinary by aircraft manufacturers. As such, a more conventional approach was taken, with the final design using a V12 layout with 4 valves per cylinder and sodium-cooled exhaust valves. Early versions also attempted to change RR's typical practice of using straight-cut propeller reduction gearing, instead opting for helical gears, but after several failures, the straight-cut gears returned. At this stage in Merlin development, the engine was only producing about 800 horsepower at 3,000 RPM, but not for long. Other early experiments occurred with the cooling system, which was also initially planned as an evaporative steam system, but this too was abandoned in favor of a glycol water mixture in conjunction with a radiator. Originally, the Merlin cylinder head was removable from the integral cylinder banks in an effort to increase beam strength. However, the size and complexity of the casing led to difficulties. So the Merlin once again adopted the Kestrel's type detachable cylinder bank crankcase arrangement, with the cylinder head integral with the cylinder bank. It was also at this time that Rolls-Royce began trying to implement a cylinder design that they had had good luck with on their Phantom II car, known as the ramp head. The idea was that a ramp head design could give shortened flame length and increased turbulence. However, the Phantom II used 2 valves per cylinder, whereas the Merlin used 4. And then the end result was a waste of about 18 months of development time as engineers attempted to get the ramp head combustion chamber to work. The issues that arose from the ramp head, which was essentially just a pent roof design tilted to one side, were that the exhaust valves were burning from localized detonation as well as exhaust port erosion. Additionally, at this time, the engine was also suffering from coolant leakage at the cylinder liner and cylinder head joint. Finally, after Rolls-Royce redesigned the combustion chamber, crankcase, and reduction gearing, the engine became the Merlin B, which was now producing 950 horsepower. However, the Merlin still retained the infamous ramp-style head until the Merlin F, which became the first production Merlin. In the mid to late 30s, the Merlin was in trouble. Because of its early teething problems and the fact that it failed its first 50-hour civilian type test, opinions were beginning to shift towards the idea that the Merlin would never be a successful engine. However, soon war clouds were on the horizon, and with the government desperately needing engines for the fighters, they relaxed the standards, and the Merlin was able to pass a 100-hour test, but problems still persisted, and it wouldn't be until November 1936 that the relaxed type test was passed. It was overcoming this obstacle that was probably the climax of the Merlin story, but it wouldn't be until about 4 more years of development that all problems were dealt with properly. To get there, the company had to finally admit that the ramp-style head had to go, and instead they recycled the Kestrel-style head. By 1940, the Merlin was on the home stretch. It still retained the one-piece cylinder bank and cylinder head, but it had crossed the 4-figure barrier and now was rated at 1,030 horsepower on 87-octane fuel. When 100-octane fuel finally arrived, the more aggressive tune that was possible allowed a rating of 1,160 horsepower, which was later advanced again to 1,310 horsepower at 3,000 RPM. While these incremental improvements seemed to be only slight, they were absolutely pivotal for the Spitfires who were now involved in the Battle of Britain. Prior to the introduction of 100-octane fuel, the Bf-109E had a slight advantage over the defending Spitfires and Hurricanes. However, these improvements helped close the gap, and according to some reports, shifted the advantage to the Spitfires' side. Around this time, most but not all of the development problems had been overcome, and it was now a question of manufacturing enough Merlins to supply the war effort rather than troubleshoot engineering issues. To this end, great effort was put into salvaging engines that would have normally been considered too damaged to be repaired. Engines that had been skewered with bullet holes were patched and repaired. Cracked crankcases that had been damaged in gear-up landings had steel braces installed in order to strengthen them for reuse. And in the case that parts were not deemed to be sufficient quality for reuse in aircraft, they were instead recycled into the Merlins used for Cromwell tanks, which were now being known as Meteors. Now, in terms of generational leaps for the Merlin, another huge leap forward would come at the hands of a man named Stanley Hooker. Hooker, who had joined Rolls Royce in 1938, was an Oxford graduate and a trained mathematician, with a postgraduate in fluid dynamics. Likely because of his training, he soon realized that all of the calculations which had been performed by the Royal Aircraft Establishment were based on formulas that Hooker determined were incorrect or suspect. As a result of his findings, Hooker completely redesigned the supercharger, which was first used in the Merlin 20, used in the Hurricane, and the Merlin 45, intended for use with the Spitfire. The first redesign was a single-stage two-speed supercharger, while later a two-stage system would also be developed. In the two-stage system, a step-up spur gearing was employed with multiple clutches used in the second gear train. As Hooker experimented with supercharger redesigns, he discovered that the intake elbow for the Merlin II was pretty restrictive, and in order to optimize it, he turned the carburetor 180 degrees so he could fit a much smoother 90-degree turn pipe onto the engine. Further supercharger improvements were also made to the impeller, diffuser, and volute housing. When all was said and done, the Merlin had now advanced from 1,310 horsepower to 1,480. And these changes also resulted in a new variant of the Merlin, evolving from the Merlin 3 now to the Merlin 45. Interestingly, some of the first Merlin 45s were put into Spit 5s and intended for low altitude work. As such, 3/4 of an inch was machined off of the overall diameter of the supercharger impeller, and the airframe of the Spitfire was modified by removing the wing tips. As many of these Spitfires and Merlins were already well loved by the time they were modified, these low-altitude Spits were sometimes given the nickname clipped, cropped, and clapped. The Merlin would officially start using a two-stage system in the Merlin 60, which was an answer to the government's requirement for a high-altitude engine that would be installed in the Vickers Wellington. As the bomber was intended to bomb from 40,000 feet, a two-stage system would be necessary to power the bomber, but the aircraft was not put into production. But it really didn't matter, as the definitive Merlin had been born. In 1941, the first German Focke-Wulf 190 stunned the British, who were still using the Merlin 45-powered Spit 5s. Unable to outrun or outclimb their opponents, a redesign of the Spitfire was required. And the answer was a Spitfire with a Merlin 60, which would become known as the Spitfire 9. The end result was a Spitfire much more capable of going toe-to-toe with the 190s. However, with all this increase in manifold pressure, it was soon realized that charge heating from intense compression was becoming a power-limiting factor. The answer to this problem became another one of Hooker's contributions to the Merlin program. Using research material from the RAE, Hooker designed a light, compact, liquid-cooled aftercooler consisting of a fin and tube radiator matrix mounted on the discharge side of the second stage blower. The intercooler simply consisted of a cooling jacket surrounding the space between the first and second supercharger stages. To cool all of these components, a new cooling system was developed that featured a centrifugal pump that pumped the glycol water mixture through the intercooler, then to the aftercooler, and finally to the main radiator, before being returned to the suction side of the pump. Now, because the Spitfire had two radiator arrays, it had lost its asymmetric look, with equal-sized radiators beneath both wings. For clarity, each wing had a main coolant radiator, with either an oil cooler or the intercooler-aftercooler combo radiator alongside it. In a move that would become typical of Rolls-Royce, rather than redesign a new supercharger system for their two-stage variants, the supercharger impeller from their abandoned X-24 Vulture engine became the first-stage impeller, and another impeller from the Griffin II became the second stage. With all these redesigns to the cooling and supercharging systems, the Merlin 60 had evolved once more to 1,560 horsepower at 12,250 feet. However, with this new power came issues with reliability, particularly in the main bearings. The solution, however, was elegantly simple. Rather than use a typical method of crankshaft lubrication such as galleries, in which machined holes in the main bearing match up with those drilled in the crankcase to transfer oil, as well as another set in which oil is transferred from the main bearing to the rod journal through holes drilled in the crankshaft, the 100 series Merlins used what was referred to as end-to-end lubrication. In this system, oil was fed into the crankshaft from both ends. This offered the advantage of eliminating the need to drill a hole in the main bearing, and it meant that centrifugal force aided the oil pressure instead of the oil pump having to fight it when moving oil into the main bearing. Additionally, the new Merlins also used small pipes that were press-fitted into the journals of the hollow crankshaft throws. In this way, the sludge that had been collecting inside them would be slung to the outside walls of the journal, but kept away from the bearings. With all of this tedious work to find innovative ways to counteract the stresses of high engine output, the Merlin, now on 150 grade fuel, began generating over 2,200 brake horsepower, which was nearly 3 times the original design goal. Before we get started in the real dense stuff of today's material, I want to give a shout out to one of my main sources, which is the book Allied Aircraft Piston Engines of World War II by Graham White. It's an excellent book for any of you to check out if today's video just doesn't get dense enough. So overall, as we'll see, the Merlin was successful because it was a conventional tested design that was improved through an iterative process. While other contemporary companies were trying out radical new designs, attempting to set a new status quo for power output, Rolls Royce was the company delivering a reliable product with tested technology. Overall, the Merlin was a 60-degree V12 with a 120-degree crankshaft, 7 main bearings, and 6 crank pins. Each crank pin had a blade and fork-style connecting rod, as far as degree spacing was concerned, the spacing was designed so that even firing occurred about every 60 degrees. The crankshaft itself was a 500-pound chrome molybdenum steel alloy that was eventually worked down into a 120-pound crank after all the manufacturing processes were finished. To complete the crank, the entire surface was machined for high finish to fight fatigue. All of the journals were bored internally to reduce weight and plugged with plates attached through bolts. Also, 4 first-order counterweights were designed in, 2 on each end and 2 in the middle. The pistons themselves were conventional aluminum forgings with 3 compression and 2 oil control rings, with most of the piston ring development being borrowed from the R engine development. The crankcase was 2 aluminum castings. The upper crankcase provided support for the 7 main crankshaft bearings, with the main bearing caps attached by 2 bolts. For additional rigidity for this heavily loaded component, cross bolts, 2 per main bearing, ran through the engine, which resulted in 28 long studs, 14 per side, screwed into the top face of the upper crankcase. A wheel case housing at the rear of the engine contained the drive gears and clutch packs for the supercharger. The 2-stage Merlin required 400 horsepower just to drive the supercharger, so designing a supercharger drive assembly that was dependable and light had proven to be a challenge throughout history. In the case of the Merlin, it used a torsionally flexible quill shaft driven from splines machined inside the number 7 main bearing journal, which in turn drove the supercharger drive gears. The quality of these gears were well known, even to the Germans, who would often use the gear unit to test turbo supercharger compressors for Daimler-Benz and Junkers engines that had been salvaged from the wheel case assemblies removed from downed aircraft. One of the primary weaknesses of the Merlin was the design of the upper and lower drive shafts. As the upper vertical drive shaft transmitted power to the inclined drive shafts that in turn drove the camshafts, a bronze skew gear about halfway up the vertical drive shafts drove the magnetos. The issue became that failure of this skew gear would result in a total power loss to the engine because ignition would also be lost. Initially, designers believed that because the gear was so substantial, it wouldn't have any issues. However, severe torsional vibration from the cam drive, as the cam lobes came over the top center on the rocker arm pad, caused fatigue and failure of the gear. In terms of controlling the 2-stage supercharging system, a directional control valve for the speed change mechanism was housed at the bottom of the wheel case. In this system, an aneroid valve sensed altitude and shifted blower speeds at the appropriate time. However, to ensure the supercharger didn't bounce between FS and MS at critical altitude, a buffer was designed into the system, which required a descent of 1,500 feet before a speed change would actually occur. The cylinder heads used aluminum castings with skewed and shrunk steel valve seats, cast iron inlet valve guides, and bronze exhaust valve guides. The valves themselves were KE965 forgings, with exhaust featuring a protective coating of bright ray, which was composed of 80% nickel and 20% chrome and applied by using an oxyacetylene torch. The exhaust valves were also sodium-cooled, a development that ensured the Merlin would never be forced to contend with sleeve valves. Each cylinder head mounted a single overhead camshaft, which ran in plain bearings. The cam actuated the valves via rocker arms, which pivoted at one end, and the opposite end opened and closed the valves. The cam lobes ran on a hardened pad approximately centered on the rocker. This arrangement was the Achilles heel for the Merlin, as it was prone to excessive wear due to the tremendous bearing loads imposed on it. The rocker pad had a hard chrome surface. However, unless the grinding operation was closely monitored, the chrome would flake off. At the supercharger side of the head, a plain bearing was incorporated for the bevel gear driving the camshaft. 2 spark plugs per cylinder were used, one on the intake side and one on the exhaust side. Because the intake side plugs were extremely difficult to change, however, it was common for ground crews to only change the exhaust plugs prior to every combat mission. The cooling system was essentially conventional, using a centrifugal pump gear driven from the wheel case. Coolant was distributed to the outside of the cylinder banks, and as such, the system used a parallel flow of coolant through the engine rather than a serial flow. For intake air and fuel mixing, the Merlin used a 2-barrel SU carburetor with automatic boost control. As overboosting was a constant threat at low altitudes on early models, and fighter pilots had more to worry about than constantly monitoring their manifold pressure, RR developed alongside the RAE an automatic boost control that allowed the pilot to firewall the throttle without concern for overboosting. This was accomplished by using a servo system that read manifold pressure and opened the throttle butterflies far enough to give the max rated boost and no more. As the aircraft climbed and the boost controller allowed the throttle to open until the critical altitude was reached. A weakness of this system, however, was its notorious lack of ability to handle negative G-forces, which would result in power loss and potentially even an engine shutdown. In the case of the engine shutdown, it was actually a 2-stage event. At the onset of negative Gs, fuel was forced to the top of the float chamber and the main jets were exposed to air, which caused a momentary lean cutout. However, if the negative G continued, the floats reacted to the reverse conditions and floated the wrong way to the bottom of the chamber. This caused the needle valve to open wide, allowing full fuel pressure from the engine pump to flood the carburetor. In turn, this excessively rich mixture was administered to the supercharger, which caused a more serious rich cutout. Because of this, pilots had to make sure that they always maintained a positive G, which, for those of you who have played a World War II flight sim, will already know that that's a huge disadvantage. To remedy this, a woman named Miss Beatrice Tilly Schilling, who was a young physicist working for the RIA, developed a restrictor that limited the flow to only the amount of fuel needed to satisfy maximum engine output and no more. Additionally, a flange was incorporated at the tapered end of the needle that created a flow restriction if it was exposed to negative G. So, yeah, that's the nitty-gritty behind the design and development of the Merlin. Now let's talk about some of the applications and wrap things up. Now, normally this section of the video would go into some serious depth concerning the development of the Merlin-powered aircraft. However, in the case of the Merlin, we'd be here for another hour discussing just that, because in no uncertain terms, the Merlin became the default engine for the Allied war effort if the aircraft intended to use a liquid cooling system. Powering the Supermarine Spitfire, the Hawker Hurricane, the P-51 Mustang, the Avro Lancaster, the de Havilland Mosquito, the P-40F, the Fairey Barracuda, and the Armstrong Whitworth Whitley, to name a few, the Merlin kind of became synonymous with reliability and high power output in a compact package. So we know about the development and the design of the Merlin from inside and out, but it's not until we put it into context that we can really know what made the Merlin special. Why did it become known as the engine that won the war? Honestly, in my opinion, the answer is because it was there and it worked. It wasn't the most fascinating original design, nor was it the most powerful engine, but it was one of the most reliable available engines, and its 2-stage supercharging system allowed it to achieve competitive output at all relevant altitudes. While Napier and Bristol had taken on extremely aspirational designs with the Sabre and the Centaurus that would have ultimately proved to be groundbreaking when their designs were fully fleshed out, Rolls Royce had no such teething issues, as the Merlin's troubleshooting phase of development had been pretty much completed by the onset of the war. In this way, the team at Rolls-Royce was able to enter a development process that consisted of just increasing the boost pressure whenever power output needed to be increased, and then subsequently resolving the fatigue issues that would crop up, which they could easily do as they had all the experience from developing the R engine. So, to put it concisely, from 1939 to 1943, while all the other British engine manufacturers were simply just trying to make their engines work, Rolls-Royce was on the scene, delivering reliable, ass-kicking power, and as such, their engines would power most of the planes that would ultimately win the war.